Okay, so today we are going to just see how to do the quotient level problem for the Quasilinear first of the partial differential equation. So we just show one problem and then we will just give the strategy for solving the result problem. Just like an algorithm thing we already did for the semilinear and the linear part of the PDE, but here we will do it for the Quasilinear. Okay, so this is the example. If we have to solve this equation, you can easily see it is not at all a linear, not at all a semi-linear, but a quasi-linear first order partial differential equation. And this is the initial part of the data. That is the data curve you can easily understand is from here to zero. So we are actually considering the x-axis and actually not the whole x-axis, but a portion of it, the 0, 1 interval. Okay. So comparing the standard form, the A u express dy equals to c, you can easily get dx d sigma equals to 0, dy d sigma equals to 1, and du d sigma equals to 0. And if you recall back to for quasi-linear, we need to take all these three systems coupled together, not only this two, as we usually did for the semi-linear, because now you can easily see u is involved. So actually, this is giving what? The longest direction it is. Okay, the longest curve we will get from here, the gamma curve. Okay. So from here only you can see we simply use coming to an arbitrary constant C1. And from here, if you get u equals to C1, I can easily put it here. So dx d equals C1 and dy d sigma is 1. Okay. So again, from here, if you just integrate and you can find out one two parameter family of curve, not a single parameter. C1, C2, both are arbitrary constant. So two parameter families of longest curve, the longest curve, and this is the longest direction. Okay. So longest curve, as I said, these are coming to be the longest curve. I am putting it in a parametric. You can easily see I have inserted the sigma instead of cy, c1y minus x equals to c2 and u is equals to c1. I am combining all these three together to give this parametric form of the longest curve. Okay. And now what is the initial data curve? Initial data curve, as I said, the portion of the x-axis. So x equals to eta, y equals to 0. The portion being given by eta belonging to 0, 1. That is the 0, 1 interval. Okay. And over this capital gamma, the initial data curve, u function of eta equals to eta, as we have already provided with. Okay. U x equals to x. Okay. So now what we will do the same thing. We will find out the point of intersection between gamma, capital gamma, as small gamma, that is the longest curve and the initial data. Okay. So from there, I am getting here, you can see P as the point of intersection, x1, y1, u1. You just try to compare with the semi-linear case. Here also we consider the intersection between characteristic curves and our initial data curve. Here we are considering the intersection between longest curve and the initial data. Okay. So any member among this curve, one member actually is taken and capital gamma is initial data curve. So SP lies on initial data curve. So you will get all these three things together. Again, SP lies on any of the longest curve for sigma equals to 0. Then from there, I get this one, x1 equals to minus c2, because you see what is the form of x on the longest curve, c1 sigma minus c2. So again, conventional thing I am using is sigma equals to 0 at the point of intersection with the initial data curve. So x equals to minus c2, y equals to 0, e equals to c1. So y equals to 0 already tallies at the point of intersection, but we are getting the initial data curve. U is equals to c1. So u eta 1 becomes equals to c1. This one. Okay. So here we are getting c2 replaced by minus eta 1 and c1 replaced by eta. So just recall back whatever we are just now putting back all the c1, c2 which we have obtained in terms of eta 1. So x turns out to be eta 1 into sigma plus eta 1. So you can just simplify it together to bring it like this. So eta 1 comes in terms of x and sigma and y equals to sigma, u equals to eta 1. So to eliminate, you can easily find what to do. The sigma and eta 1 will be eliminated. You can just put u equals to eta 1 equals to this. Okay. Sigma is equal by y. So ultimately you get this one. So this is the required solution surface for the given data curve. Okay. So what are the implications we are getting from here? For every fixed zero, for every fixed u, that is for every So what are the implications we are getting from here? Okay, for every fixed q, okay, that means if I fix the solution surface, the solution surface value actually, if it fixed q, what can you consider? The u is fixed some numeric value. So x equals to y plus 1 into that numeric value. Okay. That is along each member of the characteristic family, u is remaining fixed. Right? Because u equals to say 0.1. So x equals to 0.1 into y plus 1. So that represents a characteristic because if you recall back, we always said key, what are the characteristic curves? The projections of the Monges curve on the xy plane. It means xy plane means what? X and y will be there, u is some fixed value. That means either on xy plane or any plane parallel to the xy plane. So if I put exactly equals to 0, then the xy plane, if I put u equals to 0.1, then a plane parallel to the xy plane where only this x and y is varying. So we are calling it roughly as xy plane. Okay. So for every fixed u, you are getting a member of the characteristic family. That is, if I fix the u, what is happening? I am getting a characteristic cast. Okay. So along the characteristic, throughout the characteristic, u is taking that. So suppose x equals to uy plus 1 with y, u putting different numeric values. That means if I consider this in the xy plane or any plane parallel to the xy, you can get this line. You see, any numeric value you put, you can easily find this. All of them passing to the point 0 minus. So 0 minus 1 and upon 0 minus 1, all these characteristic curves are coincide, right? So this is actually a point of singularity. In this case, for the specific problem we have dealt with, we are getting across a point of singularity that is given by the point 0 minus. And the domain, you already know it, even then I have just kept a note separately. The domain D in xy plane the solution is determined depends on data prescribed in the Cauchy problem. Quite obviously. If in the xy plane means where if we are considering some fixed value, we can easily understand if this solution is, or rather from the solution, we have used the Cauchy initial value or Cauchy data curve, right? So if I change the data curve, the change will be reflected in the solution surface. And if the solution surface differs, then for different values of u, I'll be getting different characteristic members. And the whole family of characteristic members will differ if the form changes here. Okay. Let us consider another example that will help us to understand more easily. So suppose u is equals to half for the same initial letter curve. That is x equals to eta, y equals to 0, equals to half. Eta varying between 0 and 1. So again, just following the same steps that we have just done, we can easily find u x of minus y by 2 equals to half. So along this curve, u is taking the value half. Okay. So that means what we are getting, the family of characteristics are given by this. For if we involve eta up to that step, and then for eta 1 equals to 0, y minus 2 is equals to 0, for eta 1 equals to 1, y minus 2 is equals to minus 2. That means, and eta 1 is what? Eta 1 can take any value between 0 and 1, nothing else then. So for 0, for 1, and for any value between 0 and 1. So these are all the possible cases, and no further cases possible. So, okay. So what we are doing, we are punching out, rather sorting out all the characteristics. So y minus 2x minus 2 eta 1, any line parallel to y minus 2. So clearly, you can easily understand slope remains same, only this changes, that is intercept from changes, that means you are putting one after another line parallel to y minus 2x. Okay. So these are actually what you are putting. This is the result of the whole bunch of the characteristic curves which are found for different values of u, and across any of these curves if you take for this curve or for this curve or for this curve. What did we obtain? We obtain u function of x minus y by 2 equals to half. That is, whenever x, this input is of this form, e will take the value. Input is of this form is what? You can simply say this is nothing but the y minus 2x equals to 0 line. So along this characteristic form, y minus 2x equals to any value. Okay, u is remaining fixed equals to half. So as I said, our main motive was to show the initial data type is playing a big role over how we are finding out the domain in the xy plane, where the your solutions are you are fixing some solution value of u fixed, and you are getting the characteristic class. That domain of the characteristic class depends on the initial data card which you are provided or which you are using to solve the problem. Okay, so this is it. So from here, let us have a, as I said, here an algorithmic sort of strategy to follow whenever we do the Cauchy initial value problem for the first order PDEs. And just straightforward, just like the semi-linear. Only as I said, there is some fundamental differences. So this is the thing we will get as among these directions. Okay, we have to consider all these two together, unlike in civilian. So as you consider all these two together, what we actually did, if you recall that what we did in the problem, is integrated it twice. So as to get two parameter families. These are the things which are getting. I am writing the parametric form. So sigma is there as a parameter of the family, sorry, parameter of the path. Okay, and C1, C2 are what? C1, C2 are the arbitrary constant. That means they will change with the change in the family members. Okay. And along the capital gamma, that is initial data curve, the data curve is given by this thing. Now it is a curve in 3 dimensions. So x, y, u, three coordinate, three components will be there for any point. So these are the components. Okay. They are again functions of some parameter which is characterizing this initial data curve. So a parameter of eta, if I consider, so x function of eta, y function of eta, u function of eta. Of course, these forms of the functions will be different. Okay. Then what we do, we are using the point of intersection between capital gamma and the longest sub gamma. Okay. So at the point, as it is in gamma, capital gamma, you can go like this. Again, it is in gamma, that is a small gamma, that is among any of the longest sub for sigma equals to 0. That will allow you to write this because G1, G2, G3 you already considered for this one. You just put simply put sigma equals to 0. Or as I said, if you do something unconventional, you can put sigma equals to sigma 0 also. Okay. Throughout sigma 0 will remain in the solution in that case. Okay. So here you should just put it here like this. So V4, V5, V6 are coming. And now what we need to do, one thing I have just jumbled up with the notations. It will be U1, okay, not Z1. So once you get these things, you just put everything back here because C1, C2, our main motive was to determine or rather find out C1, C2 in terms of eta 1 sigma. Okay, so we have done this. We can easily eliminate sigma or eliminate means we can easily find out C1, C2 in terms of sigma and X, Y, whatever. So if I put everything back together, okay, C1, C2 eliminated. So ultimately you will get something in this form. Okay, G7, G8, and G9. Okay. C1, C2 are getting determined, so I am just considering this is the form which will come there. So I should be more precise. I did another thing very loosely here. It should be some function of eta 1, G7 eta 1, and G8 eta 1. Again, this one G7 eta 1, G8 eta 1. Then this one also G7 eta 1, G8 eta 1. Not three different things. Because C1, C2 are the same for its value, right? For the quite obvious. So it should be say suppose C1 is coming out to be a function of eta 1, G7 eta 1. C2 coming out as a function of eta 1, G8 eta 1. So what should we do? We should take everything here and replace it. So C1 will be replaced by G7 eta 1, C2 by G8 eta 1. Again, here G7 eta 1, C2 replaced by G8 eta 1. Here also G7 eta 1, here also G8 eta 1. So the question of G9, G7, G8 will come in each of them. So once I got everything in terms of sigma and eta, what will happen? You can eliminate them. First to find out EXY equals to some value, not 0, but any other value may come here. I have again, this is typo. It can be any real. Okay, so this is the liquid solution surface. And one thing let me remark, I just point out here, is if you follow the non-conventional way of not putting sigma equals to 0, but putting sigma equals to some specific value sigma 0. Remember that is a constant, right? So it will remain throughout your solution. It will remain here. You cannot eliminate that from there. So there is a fixed value we are considering. So it will remain here. So let us stop.